number of you. So one possibility is I could just leave today and come back tomorrow. Yeah. No, but I'm going to present it in a way which is maybe slightly different from the way you already learned it. So if you just, flush your minds of what you already know, just for the sake of learning it a different way, it might be useful to you to learn from a different point of view. And those who haven't had any exposure to the theory, that would be fine too. You're just learning it a different way from what you will learn later in your course. Now, I'd appreciate having questions while the talk is going on, because then I know how much is getting across, okay? And when you have a question, you just raise your hand and take the mic so that people who are online also get to know what the question is. Yeah, maybe these can be passed around. So that's my title, The Special Theory of Relativity. And that's I used to be here, and now I'm at another place. So the first thing to understand is about the speed of light. The speed of light is a large number in everyday units. Kilometers per second, it's about 3 to the power of 3 times 10 to the 5. That's a very high velocity. It's much larger than any velocity you see around you, like cars or airplanes or anything like that. So it's very large in everyday terms, and it's practically infinite, because the ratio of a car, the velocity of a car divided by the speed of light is so negligible that you can forget about it. So Newtonian mechanics does not have a role for the speed. It was implicit in Newton's thinking that signals can be sent at any speed. The first evidence for finiteness came from astronomy, and this was due to a Danish astronomer called Ole Rømer. In 1675, he was studying the eclipses of a moon of Jupiter, and he was doing this for a very practical reason. There was a problem of determining the longitude of a place. That's another story which is fascinating, but I don't have time to go into it. But he found that the eclipses of Io, the moon of Jupiter, well, normally they take, according to Newton's laws, they take about 42 hours to happen. Every 42 hours you see an eclipse. Eclipse is when the moon goes behind the planet and comes around and goes back again. So he was trying to get the exact time of the eclipses. How long do they happen? It normally takes about 42 hours and a half, 42 and a half hours. And he got a very good clock designed by Huygens, Christian Huygens of the the famous name anyway. And he was measuring the time, and he found that there was a small discrepancy of about 13 seconds when the Earth, maximum of 13 seconds, when the Earth was moving towards Jupiter, it came slightly faster, and otherwise it came slightly slower. So the time of the eclipse seemed to vary, and it was a small amount, 13 seconds in 42 hours. Anybody else would have said, oh, some problem with my clock or something. He had confidence in his clock, he had confidence in Newton's laws. He pursued this and found it was because of the finite light travel finite time taken for light to travel from Io to us. So essentially what is happening, there's a certain period, and that period gets stretched out depending on where we are on the Earth's orbit. When we are nearer to Jupiter, the eclipses come faster. When we are farther away, it comes later. And that distance, he calculated it by means of his observations to about, that light takes about 11 minutes to traverse the Earth-Sun distance, which is a pretty good number given that time. Now, the head of the observatory was Cassini. He was initially skeptical. He believed that light traveled at infinite speed. He didn't believe Rømer's results. But then he slowly convinced himself and improved on the observations and came out with the answer of 8 minutes for the light travel time from the sun to the Earth. Now, this simple fact that light travels at a finite time led many years later to the theory of relativity. That's what we're going to talk about today. By the way, this whole thing, if you just look it up, it's fascinating. It brings out many points about science. One is the confidence he had in Newton's laws, in the existing laws, and tried to apply them and see where they break down, and in his own clock and his own measurements and all that. The other thing is that Cassini is the head of the observatory, and the head should have been the boss, but he was not the boss. He eventually got convinced himself. So there's no authority in science. A young person can make a discovery as well as an older person. So I'm going to give two talks on relativity, the special theory of relativity and the general theory of relativity. Today is only going to be the special theory. This is a rough plan of my talk. Introduction, then I'll derive the Lorentz transformation and some of its consequences. Finally, I'll show you that it agrees with Newtonian relativity in a particular limit when the speed of light is taken to be very, very large. And then I'll set the seeds for tomorrow's talk in presenting physics as basically geometry of space-time. And I'll stop with a conclusion. I'll try to tell you where you're likely to encounter relativity when you do your astronomical studies. In fact, there I'll try to get the answers from you. So in physics, we deal with many things like motion, force, energy, planets, atoms, and we are used to studying many things in the laboratory. The underlying space-time is the arena or stage in which the drama happens. So everything that happens, happens in space and time. So we need a good understanding of the stage, that is the stage in which the drama happens, and that is empty space-time. So the principal experimental fact that we're going to use is that the speed of light is finite, and secondly, that it's the same for all inertial observers. It doesn't matter at what speed you're moving, you still measure the same speed for light. That looks very counterintuitive, but it's a fact. And it's been tested time and again in the Michelson-Morley experiment. So the C is actually a fundamental constant of nature, and instead of calling it the speed of light, I could call it the speed of gravity or the speed of neutrinos or, no, speed of any massless particle. The main message of this talk is that space and time are really the same stuff. We think of space and time as completely different, and that is because we're used to measuring time using clocks like that one, and we're used to measuring distance using rulers. Has somebody got a ruler? Okay, somebody does have a ruler. So both things are useful in everyday life. We use time, we use our clocks to measure time, and we use rulers, here's a ruler, to measure distance. Yeah? So the first objection to this suggestion could be that they have different dimensions. They cannot be the same thing. But then we must remember that the speed of light is there, and we can convert time into distance and distance into time by either multiplying or dividing by c. So we can keep the clock, and we can dramatically dispose of the ruler by converting everything into time units. To measure how far the room is, I mean, the end of the room is, I'll send a light signal from here and receive it back. And when it comes back to me, I'll measure the light travel time. From that, I know the distance, right? So here, we don't need the ruler anymore. Yeah. So the point here is that we use only clocks, and we don't use rulers. We don't need to use rulers because we have this wonderful object that nature has given us, the fundamental constant, which is the speed of light. So in order to understand the nature of space and time, we need basically empty space-time, but we will need a few things to do our experiments with. Firstly, we need to be present. We are observers. We'll remove all matter, which we don't need, except light and except clocks. So here's a clock, for example. All of you have one in your pocket. Yeah? And there's a clock. We have clocks and we have light. So what you do is you measure distances using light travel time and get a good clock. I mean, these clocks are decent, but there are better clocks. For example, there are cesium clocks, which you can use to measure time to greater accuracy. And actually, if you look at, if you visit a laboratory, as there are many here, you'll realize that experimenters always like to convert everything into time measurements. Time is the most accurately measured quantity. Here's how we'll do it. We'll set up a coordinate system. This is space and that is time. And this is one observer A. We can call her Aisha. And then to determine the coordinates of this point here, this is an event. Sorry. Okay, this is an event. Every point in space-time is called an event. For example, an event could be a snap of a finger like this, a particular thing that happens localized in space and in time. It's like a point in geometry, and we'll come back to that later. So she sends out a signal at time t1a according to a clock. The signal glows at 45 degrees because I've taken care to divide this by c. And it goes to that event, and let's suppose that somebody else is there with a mirror to send it back. So it goes there and it comes back. And she makes a note of T2A, the time when it comes back. Now you believe that it takes as long to get there as to get back. So the average of the two times is the time I would assign to this event. And since in going there and coming back, it's traversed twice the distance, I take the difference of these two numbers and divide by 2. So I assign coordinates XA and TA according to these formulae. Is that clear? Absolutely clear.
So both the axes are time.
Yeah, I think you should use the mic. Yeah, you should use the mic.
So both the axes are time.
Yeah, that's right. So the x-axis is converted into time units, but it's supposed to represent space. So we won't distinguish between space and time. We just convert from one to the other. Yeah? This is more like geometry. Now, suppose there are two observers. One is Aisha, who's done this experiment before and arrived at her assignment of coordinates to this place. And the other observer is Balachandran, B. And he follows this world line. Let's say that when they meet at they synchronize their clocks. So both their clocks read 0 at the origin of this graph. And then after that, B goes on like this, while A goes on like that. And we can use the same signals that were sent. So this ray of light came here, went there, came back. This point now, according to Balachandran, is T1b, and this point is T2b, when the light ray went there and came back. Right? And it's very clear from the Doppler shift. This goes back to Romer now. When Romer saw that the frequency is more when you're going towards the source and less when you're going away from the source, time gets stretched in the Doppler shift. You've all encountered this, especially during the pandemic, though I don't like to remind you of it, when there were ambulances that were screaming up and down the road, and you could hear the frequency change. But I'm going to subject you to another demonstration of the Doppler effect, because I can't do it with light because I cannot move that fast, but I can do it with sound. So this whole argument is based entirely on the Doppler shift. So I want to introduce you to a toy like this. Does anybody enjoy listening to music? Okay. So that is. Okay, now those who enjoy listening to music, you should cover your ears because you're going to hear something terrible now. Sure. No, sorry. Does it sound in tune? Huh? Yeah, that's because every frequency is stretched out by a little bit. As the sound is coming to you, the frequency is coming at a regular rate. But when the when the source is coming towards you, right, it comes at a faster rate and slower rate. So it sounds out of tune. And musicians will hate me for this, but it's in the interest of science. So the Doppler shift tells you that because B is moving away from A, there will be a difference in the time intervals. So T1b will be given by delta times T1a. This is the time as measured according to, this is the distance from here to there according to B. And you can see from the Doppler shift that there will be a stretching of the time interval because they're moving away from each other. And that stretching is a factor delta, which in this case is greater than 1 because he's moving away. If he was coming towards you, it would be less than 1. Yeah? So all of relativity can be understood from just the Doppler shift. That's the point here. So this is the way now that B will define the coordinates of the same event, TB and TXA, by taking the mean of the two times and the difference of the two times divided by 2. And this provides the dictionary between the two observers, and that is the Lorentz transformation. The Lorentz transformation, exactly these two formulae. This is the Lorentz transformation, just the Doppler shift. All we have to do now is to convert this formulae into ordinary space and time variables. So that's what we do here. We define x minus to be t minus xa by c, and that is equal to t1a, and x minus to be t minus xb over c, which is t1b, and similarly for the plus sign. And then Lorentz transformation just looks like this. X minus stretches and x plus shrinks. That's the Lorentz transformation. Now, if you multiply these two together, one stretches and the other shrinks, and the total stays the same. So you know from this, by using an elementary formula from algebra, that S, which is t squared minus x squared upon c squared, is the same for both observers, which is consistent with the fact that light moves at the speed c for both. Yeah. The mic, please.
What are xa minus and xa plus?
Yeah, xa minus is the difference x minus t minus xa over c. That combination I call it, it's a variable I define. And that is xa minus, and it's the same as t1a. Right? And xb minus is similarly defined, and similarly xa plus and xb plus.
So just coordinates.
They're just coordinates, combinations of the coordinates. So, yeah, one is right moving and one is left moving. Yeah? Yeah. And they are the directions of the if I put x minus equal to constant, that's 145-degree line like that, and the other way around. Okay. Now, suppose there were three observers. This is Ayesha, Balachandran, and Charlie. Okay? And we do the same experiment. Between Ayesha and Balachandran, there's a Doppler factor, which I call delta AB, which goes from A to B. Between Balachandran and Charlie, there's a Doppler factor, which I'll call delta BC. And it's evident from this diagram that delta AC is the product of these two factors. The stretching when you go from A to B is the same as the stretching when you go from B to C. I mean, the combination, the product of the two will give you. So this means that delta is a multiplicative quantity when you compose Lorentz transformations. A to B and then B to C, the Doppler factors just multiply. Now that is reminiscent of the ordinary velocity in Newtonian physics. If I go to a frame with a velocity v1 and then to v2, the combination goes with the speed of v1 plus v2. Yeah? But here it's a multiplicative quantity. So what do? We take the logarithm, that is, we write delta as exponential of alpha, and then we'll find a quantity alpha, which is an additive quantity. Alpha just adds. We call it the rapidity, and it's just the logarithm of delta, logarithm of the Doppler shift. We're just giving it a name, rapidity, to not confuse it with velocity. And then now if you just go back and plug in the things that we already have, you'll find that TA and XA are related to TB and XB by this simple and beautiful formula, which looks a bit like a rotation in space and time. So this is the Lorentz transformation in the way you might have encountered it in your books. Basically, it's written in slightly different notation, but you'll see it's the same thing. So if I put XA equal to 0, that will tell me the set of points where the observer B will see XA's line. And if I take XB and divide it by CTB, I'll get V over C, because X by T is V. And that gives me a quantity which I'll call beta, which is V over C. And you can see from this formula, if I put XA equal to 0 here, that beta is basically equal to tan hyperbolic of alpha. All of this hinges on using hyperbolic functions. And many of the identities that you'll encounter here, you've already seen in the context of trigonometric functions. I'm sure everybody is familiar with exponentials and hyperbolic functions. Right? For example, cos squared minus sine squared. Cos squared minus sine squared is 1, unlike cos squared plus sine squared with ordinary functions. So all of relativity boils down to getting used to these trigonometric functions, and this can be thought of as a rotation through an imaginary angle in space and time, if you're familiar with complex numbers. So all of this is useful for thinking about it geometrically. Now, if you think about space, so for example, this thing has a certain dimension when you look at it like this. But if I change the angle, the dimension seems reduced. And this is described by a transformation very similar to this. So depending on where you're looking at it from, a circle could look like an ellipse. We're used to the idea in space that different points of view, things appear different. Here, the idea is to transfer that intuition to space-time. So now we can just use our trigonometric function knowledge to write gamma as cos alpha. I'm defining it to be cos alpha. And you can easily work it out to be 1 upon square root of 1 minus v squared by c squared. And the Doppler shift itself turns out, and I'll leave all this to you, you can easily work it out, to be square root of 1 plus beta over 1 minus beta, the shift factor. Everything depends on alpha, which is the rapidity.
Sir,
Yeah.
the multiplication of the coordinates xa minus xa plus
Yeah.
equal to xb minus xb plus.
That's
Why
correct.
is that invariant?
Why is that?
Invariant, I mean the multiplication.
Okay, let me go back.
Yeah.
So why is it invariant? Suppose I look at this quantity, x minus, x minus gets an extra delta, and x plus gets one delta less. So the two deltas cancel out.
Okay, so why is it delta inverse?
For that you have to go back here. See, this was also a consequence of relativity. If we send the signal from here, if you send it from here, right? Yeah. So, yeah, if you send a signal from here, this guy will see it coming slower. I mean, the delta will be stretched out. Now, if I'm looking at this point, here A is the sender and B is the receiver. If you get over here, A is the receiver and B is the sender. Yeah? So, A will say B is going away from me, and so there will be a delta factor which is inverse of that. Yeah. Okay, let's go back here. Here, if you look here, T1B is delta times T1A. That's clear, right? Now T2A, this guy, now he is the receiver and B is the sender, is equal to delta times T2B. So if I take this equation and switch the roles of A and B, I'll get a delta inverse there. Yeah? So that was a crucial point. Thank you for pointing it out. Yeah. So it's actually the principle of relativity that tells you that you can either sit an A and think of B as moving away from you, or the other way around. Okay, so instead of synchronizing their clocks at the same time and all that, let's just take dt. So then that origin drops out. Small intervals of time dt will transform like this, and this is the Lorentz transformation. If you just put some standard substitutions here, you'll get back the Lorentz transformation that you know. And I'd like to write it like this because it brings out the geometrical notion of the Lorentz transformation as a rotation in space-time. And of course, the transverse directions are not affected by all this. And the total quantity that we call the proper time is this particular combination, dt squared minus, all these should be plus signs in here. Sorry about that. And you know from quantum mechanics that momentum is h bar over I times d by dx, and energy is d by dt, h bar over I times d by dt, or I h bar d by dt. And you can well believe that when I tell you that E and P will transform very similarly to this, and they are quantities which we call a 4-vector. Time and space form a 4-vector, energy and momentum also form a 4-vector. And the relation between energy and momentum is this one, which is slightly different from what you get in Newtonian physics. So maybe I'll pause here for questions before I move on to all the consequences of the Lorentz transformation. Okay, everybody's fine? Okay. the first thing that we learn is that if I put dxa equal to 0, that means that dxb is also equal to 0, for both for the plus and the minus dx's. So that means that light ray stays the same. That's what we had put in. So that's something that comes out of this Lorentz transformation. But what is not true is that the notion of simultaneity does not stay the same. If I go to the Lorentz transformation and put dA equal to 0, it does not imply that dTB is equal to 0 unless they are at the same point. That is, dXB is also equal to 0. So that's the first consequence, that simultaneity is no longer absolute. In Newtonian theory, simultaneity was absolute, but that's no longer true. The next consequence is time dilation. So if you have this is Aisha and this is Balachandran, and this person has a clock which is ticking at regular intervals along his world line. So what is the time difference between these 2 points as seen by A? It's very simple to work out from the formula that we have, and you find that the time is actually stretched. dTB is dTA times cos alpha, and that cos turns out to be this quantity. Now, a slightly different idea is that suppose in B's frame, there is a rod. So this is the world line of B, and this is A, and there's a rod in this guy's frame. The two ends of the rod are what I've drawn here. So B will say that the length of the rod is what is given by points where the time coordinates are the same. So that will be some 2 points like that. But A will say that the 2 points at the ends of the rod are where TA is equal to 0. So this guy will put dTB equal to 0, and this guy will put dTA equal to 0. So they're actually different events. When you do that calculation, which is quite simple to do, you find that the contraction of lengths, a moving rod appears to be shorter than a rod which is at rest. Right? And another thing that comes out very simply from this is velocity addition. There's a formula for the tan theta plus phi, which is tan theta plus tan phi upon 1 plus tan theta tan phi. So we already realized that alpha is an additive quantity. So if we just take this and supply some tan hyperbolic of alpha 1 plus alpha 2, that is equal to tan hyperbolic of alpha 1 plus tan hyperbolic of alpha 2 divided by 1 plus tan hyperbolic of alpha 1 times tan hyperbolic of alpha 2, which if you convert it to velocities, you find that it's equal to v1 plus v2 over, sorry, there's a plus there but a minus here, 1 minus v1 v2 upon c squared, and this thing divided by c. Sorry? Oh, first it's minus, then there should be plus. Is that right? Is that right? No. Let's see. Let's see. Oh yeah. No, there should be minus. It should be minus. Yeah, they're both minus in this sense. Yeah. So in fact, when you add the velocity, suppose you take this formula, if you put v2 equal to the velocity of light, you find that the sum is still the velocity of light. C plus v basically gives you back c. So let me give you a slight bit of homework. You can derive this thing by pretending to have a clock. A clock is a very simple object. Normally they take a cesium atom, but I can just take two mirrors of a fixed distance apart and send light up and down. So if that clock is at rest in my frame, there's a certain frequency. But if it's moving uniformly, I will see the light going like this, right? And you can calculate the period of that law, and you'll find that it follows exactly the time dilation formula. And one observation that confirms this theory is that there's a elementary particle called the mu meson. It appears in cosmic rays quite a lot, and they come in at relativistic speeds, these the mu mesons. And in their rest frame, they have a very short lifetime of 10 to the minus 8 seconds. But they're able to come all the way to the surface of the Earth, and we're able to detect them. So in our frame, they have a much longer lifetime than they do in their own rest frame. That's an example of time dilation. So this is one of the vindications of the theory of relativity. Okay. Now, this is a cartoon drawn by my daughter when she was about 9 years old. I like to show it off. So it's basically the famous relation E equals mc squared. And you can easily derive this from the considerations that we've been talking about. Does anyone know how to derive this? I mean, to show that E equals mc squared. So I'm going to present to you a simple thought experiment, and Einstein used to think a lot in terms of thought experiments, and that proves this fact that energy and mass are really the same thing. So before Einstein, that is in the time of Newton, we believed that there were two conservation laws. Energy was conserved and mass was conserved. Matter cannot be created or destroyed, and energy also cannot be created or destroyed. After relativity, it turns out that there's only one conservation law. A combination of energy and mass is conserved, but they're not separately conserved. So this thought experiment brings that out. So I'm going to start naively by assuming that Newton was right, and then I'll find that I'm wrong. So here's an atom, and let's say that it emits 2 photons in opposite directions, 2 photons with the same frequency. We can easily think of this happening. So this will carry away some energy and momentum, and this will also carry away some energy and momentum. But since the momenta are equal and opposite, the atom will stay at rest. So the atom before had energy E1 and M1, and afterwards the energy was E2 and M2. Now we'll invoke the conservation of energy. E1 is equal to E2 plus twice h nu, because h nu went in this direction and h nu went in the other direction. The conservation of mass will tell you that M1 and M2 are the same. And the atom is at rest before and after. Now I look at the same experiment, but from a different frame. Either I can assume that I am moving this way towards the atom, I mean from this side, or I can assume that the atom is coming towards me. In any event, I'll see a blue shifted photon here from the Doppler effect again, and I'll see a red shifted photon here. Now let me do the energy balance again. Conservation of energy and mass. The conservation of energy tells me that if I take E1 prime, which was the initial energy, now it's moving with a velocity v towards me. So there's a kinetic energy given by half m1 prime v squared. That has got to be equal to the final energy, which is E2 prime, the final energy of the atom, plus half m2 prime v squared in case the mass is changed, plus also twice h nu times cos alpha. Where did this come from? There were 2 photons. One of them was redshifted by a factor delta, and the other one was blue shifted by delta and red shifted. The other one was red shifted by delta inverse. So if I take delta plus delta inverse, I'll get twice cos alpha. I'll get e to the alpha plus e to the minus alpha, which is twice cos alpha. So this is the form. This is what conservation of energy tells me. Now I'm going to take cos and expand it for small velocities. Remember that cos alpha was equal to 1 upon 1 minus v squared upon c squared, the square root. So if I write that for small v, I can write this as 1 plus half v squared over c squared. There'll be higher order terms, but this is all I need. So I can write cos as 1 plus v squared upon 2c squared. And now if I write down the conservation law, of energy in this approximation, what I'll find that E1 prime minus E2 prime is twice h nu. Because if you go back here, there were terms that were independent of velocity. The terms that were independent of velocity are this one, and the h nu here multiplying the 1 of cos alpha. That is independent of velocity. The other terms all had v squared in it, so I can separately equate the coefficient of v squared and the coefficient of 1, because this should be true for any velocity. When I do that, I find that E1 prime minus E2 prime is 2h nu, and M1 prime minus M2 prime is 2h nu upon c squared. So the change in energy is equal to the change in mass times c squared. So that proves that energy and mass are freely interconvertible. Depending on your frame of reference, you'll either, I mean, if in a relativistic theory, you can convert energy into mass and mass into energy. Okay, now I'll pause for some more questions before I move on to. So how do you understand E equal to mc squared? Perhaps somebody can tell me. What about you?
So the energy possessed by an object
Yeah.
with rest mass m is basically.
Yeah, that's the statement, but I mean, how is it derived? I mean, there are many ways to derive it. I think this was the way in which Einstein derived it, but there may be other ways in which it's taught.
So they use the work energy theorem. I think they integrate, they find their way to
The mic, please. Yeah.
Yeah. So I think, as far as I remember, they found the change in energy by assuming a form of the energy be proportional to the some function of the mass, and try to find the work energy theorem in this case, which is consistent with the Lorentz transformation. I'm not quite.
Okay. Yeah. Yeah.
Actually, there is also another conservation of momentum.
Yes.
That was, I think, used to get that relation between relativistic mass and rest mass.
Okay. Yeah. Okay. So I'm going to talk about some further consequences of the Lorentz transformation. Here is the Lorentz transformation. And till now, we've only been talking about the Tx plane. Let's also bring in the other directions, y and z. Now, suppose there's a particle moving with a velocity v, and the x component, we already know how it transforms when you go from A to B. The others don't transform. I mean, okay, this is all we need. The x component transforms like this from the addition law of velocities. Now, if you're talking about light rays, then the x component of velocity can be written as nu times cosine of theta, where theta is the angle between the direction of my velocity and the object that I'm looking at. So I can write this cos theta as mu to save writing. And then if I go back to the formula of the last slide, I can replace this by V mu, VA mu, and this one by VB mu and VA mu. But for light, those two velocities are the same. The speed of light is the same for everyone. So I arrive at the conclusion that a light ray which is coming at an angle theta will obey this formula. The angle as seen by B is given related to the angle as seen by A as mu plus A plus 1 plus mu, mu A plus beta upon 1 plus mu A beta. Yeah? So this is the way in which angles transform, and that is quite remarkable because in Newtonian physics, the direction in which an object is does not depend on your motion.
What is beta?
Yeah, beta is V over C. Beta is V over C, where C is the C is the speed of light, and beta is the velocity of the transformation. The mu's are just cos thetas. This is the angle cos theta as seen by the first observer, and the angle is seen by the second observer. Now, what happened? I'm missing a slide anyway. So, okay, maybe I'll bring back the slide later on. So what this means is that if you look at this formula, so if I plot mu b here and mu a here, so mu b goes from -1 to +1, and also mu a goes from -1 to +1. So if I'm moving in this direction, okay. So basically what this formula tells you is that a light ray, if I'm, say I'm moving in this direction, so you're all here. As I'm moving in this direction, it will appear that all of you are shifted in that direction. If I move fast enough, you'll be practically in that direction. Because the light rays that are coming from you to me, it's a bit like when you go in a rain. The rain is coming straight down, but if you're on your motorbike, you'll feel that the rain is coming towards you. That's because the rain is falling at a finite speed. And your vehicle is going at a finite speed. That ratio will tell you the angle of the ray. The same thing happens with light. If you're going at half the speed of light in this direction, this entire room will move in that direction. And that's contained in this formula. You can see by the way that the only two directions which are left invariant are mu equal to 1 stays at mu equal to 1. If I put mu equal to 1 here, I get 1 plus beta upon 1 plus beta, which is 1. And the other point is, if I put mu equal to -1, these 2 points stay the same. And in Newtonian theory, they're equal to each other. So we draw this line. But in this relativistic theory, you find a dependence like that. So everything looks as if it's coming from that direction. Conversely, if I have a source which is emitting isotropically in its rest frame, but if it's coming towards me, all the light that's coming out in all directions will appear to be coming towards me. And that's what you can see in the next slide. This is a picture of a black hole. So it's surrounded by an accretion disk which is going round like this. This part looks brighter than that because this one is going away from us and all the light is being emitted in the forward direction. This part appears bright because it's coming towards us and all the light is being emitted towards us. So this is actually a plot made in 1979, long before computers were sophisticated and all that, based upon just integrating the geodesics of general relativity. Now for very low velocities, you'll find that the change in the angle can be approximated by beta sine theta, where if theta is equal to 90 degrees, you get a small change of this angle. And this gives rise to an apparent shift in the position of stars when you observe them 6 months apart. As the Earth is going around the sun like this, when the Earth is moving this way, the stars appear to be in a certain position. But if you measure it 6 months later, they appear to be in slightly different position. So this is stellar aberration, and it was suspected to exist by Romer, the same guy who discovered this speed of light. He looked for it, but didn't succeed, and many other people looked for it after him. But some years later, James Bradley was able to detect the small effect, 20 arc seconds. This turns out to be about 10 to the -5, which is the ratio of the speed of the Earth, which is 30 kilometers a second, divided by the speed of light. Okay, so another important consequence of relativity, the elapsed time is a path function. What I mean by that is the following. Suppose you have time here and space here, and you consider a curve. You can think of this curve as consisting of small pieces. Each of these pieces can be thought of as locally straight. Suppose I add this, suppose there's a clock that is going along this path. the interval between the ticks, each of which is very small, can be thought of as a straight line, and you add up all these, you'll find that the time here depends on the path that you took to get from here to there. So we're not very surprised about this. Suppose you take space, you put x here and y here, the total distance between 2 points in space, of course, depends on the path. And we're not very surprised by that. But the same thing is true in space-time as well. The total time elapsed from here to there is actually dependent on the path. If I take this path, the time will be different. If I take this path, the time will be different. I mean, within limits, I can't go faster than light. Yeah? So that is a rather startling conclusion of relativity. And it leads to something called the twin paradox. And those of you who have seen Interstellar know all about this. So there's a man who's young and his daughter is old because, you know, he has been through some gravitational fields and time slows down, all that kind of stuff. So I think you're familiar with the twin paradox. Now, if you take the non-relativistic limit of the Lorentz transformation, you find that after the C's all cancel out, in the limit that C goes to infinity, you find that you recover a transformation which we are used to. This is the Galilean transformation. And there is no sky distortion when you get to the limit of C going to infinity. Yeah? Sorry, no?
There are no frames.
There are no?
So if we consider it about frames, moving frames,
Yeah.
then it goes to Lorentz transformation. If everything is occurring in a single frame, then it goes for
Even if you're in a different, if I take the Lorentz transformation and take the limit of C going to infinity, what I find is that simultaneity is recovered. TB is the same as TA, and also this equation is correct. This comes out. I'll just show it to you in a second. Yeah, maybe I'll do that calculation. So I'm not saying that we are still changing frames. I should make this point a little bit clearer. So I don't remember which, okay, A here and B there. Yeah. If I take the limit of C going to infinity, what happens is that alpha tends to 0. Right? Is that clear? Because well, yeah. Okay. Going back here, cos alpha was equal to 1 upon square root of 1 minus v squared upon c squared. And if this goes to, if c goes to infinity, v by c goes to 0, this tends to 1, and so alpha tends to 0. So working in that approximation, the only thing I need to consider, I can forget about this term, it's of order v squared, but this term survives. So I'll find that, I mean, this term survives. This term also goes away because I put TA is equal to minus sine alpha. I'm sorry, this goes to 1. This goes to 1, this goes to 0 because there's a c in the denominator. And over here what happens is that this term survives because there's a c in the denominator uniformly, and if I multiply by c, I get this transformation law. So the principle of relativity was there even before Einstein. So the Galilean theory of relativity is that all observers in uniform motion have the same laws of physics and they see the same space-time. All that Einstein did was to change the law. The number of transformations was the same. So there are space-time is invariant under translations, under rotations. That is 3 plus 3, 6. And then also time translations, which is 7. And 3 boosts, 3 directions in which you can move inertially at a uniform velocity. So there are 10 transformations in both theories. It's just that the form of the transformations is different. Here it looks like time does not change at all, and only space changes a little bit. Yeah? But the Lorentz transformation changes, mixes space and time in an essential way. So before going there, let me also say that if you take the non-relativistic limit, we remember that x minus and x plus were both preserved in a Lorentz transformation. In the non-relativistic limit, what happens to x minus and x plus is that they go from being like this to being flat like this. And in the limit that c goes to infinity, they become absolutely flat. So we recover the simultaneity notion in the limit that the speed of light goes to infinity. Yeah? So we recover simultaneity. There's no Galilean, there's no distortion of the sky when you take the limit of light going to infinity. Now you can think of all this. Perhaps I should just wait for questions in case it's starting a new topic. Yeah. Yeah, just a minute.
You mentioned that there are 10 transformations, but there should be 6 only, right? 3 rotations and 3 boosts.
Yeah, I'm also including translations because translations are also a symmetry. So let's write down all the transformations. For example, x going to x plus a, that's a valid transformation. Huh? And then, so these are translations and there are 3 of them. Then there are rotations, that's basically x, y, z doing this kind of a matrix. This is equal to some r times x, y, z. There are 3 of these. That is 6, all right? And then there is also time translations, time going to time plus a plus b, let's say, and then the Lorentz transformations. So totally 10. The whole set is called the Poincaré group. It's a 10-dimensional group. And in the non-relativistic case, it's a Galilean group. So the dimension of the groups is the same. The total symmetry of space-time is the same. But the way in which the symmetry acts on space-time is different. If this makes any sense, this is basically mathematical language, group theory.
Sir,
Yeah.
so, so the straight line is the longest distance between two ends, but we learned that it's the shortest.
Yeah, right. You're right, yeah. So we learned that it's the shortest. So let me just show you why it's the longest. So that is a strange thing that, okay, let me come back to that question. So now we're going to think about physics more in the sense of geometry. So we studied in school, Euclidean geometry is given by this idea that the distance between 2 points can, or along a curve, given any 2 points, so given any 2 points, like these 2 points, if I draw a curve between them, I can split it up into small pieces. And each piece is a small bit which I can use that formula and find out the distance and add them all up. And the straight line is the shortest distance that you can draw from A to B. Right? That's what we learned, and that's correct. Nothing wrong with that. The difference here is that now we're in a new kind of geometry where there's a relative minus sign between space and time. That relative minus sign is what causes all the difference between Lorentzian geometry and Euclidean geometry. So let me show you that if I have time over here and space over here, so this is x and this is t. I can go from here to there along this line. So can I find a longer line than that? I can find you a shorter line than that. So that's done by the following way. I'll just go at 45 degrees here and 45 degrees there. This line has got length 0 because it's going along the path of a light ray. Along a light ray, ds equal to 0 because dx by dt is equal to c. So I go at 0 time like this and 0 time like that. So this is clearly a shorter path than that. And if I do any kind of a wiggle here, I always find a shorter path than this one. So the geodesic is an extremal path, but it's not the shortest path. An extremal path means that the first order variation is 0. If you consider, Mike, please. Okay, just speak loudly then.
If we are considering the time, then
Yeah.
it is a Brachis to curve
Brachistochrone is still the shortest time problem. Okay, it is a variational problem. Determining what is a straight line is a variational problem. It's described by saying that something or the other is the maximum. And all the laws of physics these days are expressed in this form of variational principles. For example, if you take classical mechanics, the principle of least action is a variational problem, right? Yeah. So in the same way here, a lot of physics can be done by just combining geometry with variational problems. Okay. Now, let me just wind up, and I want to say some general things about physics before we have a more extended discussion. Okay, this is a, yeah. So in this space, parallel straight lines will never meet. I mean, that's true here also. But it's a kind of geometry which is a bit weird because of this minus sign. And straight lines represent uniform motion, and most of the time we've been talking about uniform motion. Time depends on the path which you take to get somewhere, and it's basically the longest distance between the endpoints. That's what the definition of a straight line is in this geometry. Now, relativity alters our notions of space and time, and all of Newtonian mechanics had to be rewritten to suit these new notions. However, electrodynamics didn't have to be changed at all, because electrodynamics describes light, and it was already consistent with special relativity. And Einstein arrived at this theory by looking at electrodynamics and looking at it from different frames of reference. That's how he arrived at it. So constancy of the speed of light was already built into Maxwell's equations, so there was no change over there. What about quantum theory? Now, non-relativistic quantum theory had to be completely rewritten to accommodate special relativity. This has been done. And this led to an idea which is quantum field theory, which deals with the creation and destruction of particles. And you can create and destroy particles because if you have sufficient energy, energy can be converted into mass. Yeah? So this is a theory in which the number of particles is not necessarily fixed. It can change by creation. Particle creation is possible and very relevant. And this is one of the most successful theories of particles and fields. It predicts antiparticles, that is, for every particle there's an opposite charge particle, like the electron has a positron, and this has been seen. There's no conflict between quantum mechanics and special relativity, but there is some conflict with general relativity, and that's what we'll talk about tomorrow. Yeah, now I would just like to ask you, where do you think relativity is going to be useful to an astronomer? Okay, black holes. Shall we just start listing the thing, please? So, yeah, I'm slightly before time, but I might go slightly over time depending on how many answers I get. Okay, there? Hmm? Microwave. Micro lensing. Okay, gravitational lensing. Yeah. Then? Cosmology, yeah, good.
Direction comes to Newton's law, like precision of orbits.
Okay. Precession, okay. Yeah. Yeah, then? What about neutron stars? Stars and pulsars. Yeah? Right? And see, if you look at the effects of relativity in the laboratory, they're there. You can find relativistic effects in the laboratory, but they are very small effects. If you look at the inner shells of atoms, you find that there are tiny splittings in the spectra of atoms, and those are relativistic effects. And also, if you look at the orbit of Mercury, that is a tiny effect. So most of the time, relativistic effects can be ignored in the laboratory and also in the solar system. But when you get to astronomy, you find that the universe is a much more violent place than you imagine. When you first look up at the sky, it looks very still. But there are things called active galactic nuclei, which are very energetic sources in the sky. These are black holes which are swallowing up matter, and they're emitting the amount of light that they emit is coming from, it looks like it's coming from a whole galaxy. But it's a tiny bit, it's as big as the solar system. So those are places in which there are very strong gravitational fields. And to understand these strong gravitational fields, you need relativity, because strong gravitational fields also implies very high velocities, and you cannot ignore the speed of light. So you might find that today's lecture there was a lot more physics than astronomy. But the two subjects are very closely interlinked. For example, the impetus for special relativity originally came from astronomer Ole Romer, who, when trying to figure out a problem, figured that light travels at a finite speed. So astronomy has something to do with describing the universe, but astrophysics has something to do with understanding the universe using the physical principles that we already know. So today's lecture was more about concepts than about information. But to process the information that you get from the telescopes, you need to understand relativity. Yeah? And also to build the instruments that you use to collect information, for example, radio telescopes, all those things need physics. So there's a close connection between physics and astronomy, and it's been a very fruitful for both fields. In physics, we have some ideas like relativity, which have very small effects in the laboratory. But when you look out at the sky, these effects are huge and you cannot ignore them at all. So they are tests for the more extreme versions of physical phenomena. So maybe I'll stop with this one. I've used up my time.
Another effect, I think, that's satellites.
Yeah.
We have to correct for the time dilation.
Yeah, very good, very good. So these are also terrestrial effects. So this has to do with the global positioning system. The global positioning system is what your mobile uses when you're trying to find your way to a movie theater or something like that. So what happens is that your mobile is in contact with a number of satellites, and by sending signals very similar to what we talked about here, it's able to locate your position in space. So if you have enough satellites to connect to and enough clocks to measure the time, you can locate yourself precisely in space, just exactly as Aisha and Balachandran and Charlie were doing. Okay. Now, it turns out that the GPS will not work accurately, and you'll be completely off if you don't take into account the relativistic effects on the Earth. There are there's an effect which we'll discuss tomorrow, where clocks in a gravitational field run slower. Yeah? And as a result of that, if you don't take that effect into account, you might think that you're in Bangalore, but you're actually in Mysore, because of the mistakes that you have made in accounting for the time. So I will stop here, and if there are questions, we can carry on either outside or whatever the norm is.
So, regions are also places where you find these bizarre things like superluminal motion.
What's that?
Superluminal motion.
Yeah, there's something called apparent superluminal motion. That's what you're referring to. That can be understood without, that's not a relativistic effect. It's only apparent.
Yeah, the detection of muons on underground.
Yes, that is a relativistic effect. Yes, yes.
But actually, some processes are superluminal, but I mean, no object can travel faster.
Yeah, see, okay, let me clarify this point. See, there are effects which are apparently superluminal, which are not really superluminal. So one is what I was talking about. If a radio jet is coming towards you at 99% of the speed of light, and you're just looking at the projection, you might think from doing a calculation that is moving superluminally. It is not, and it's completely understood. Another place is that if you take the early universe and look at the expansion of the universe, you might, if you take 2 points far away from each other, you'll find that they are expanding faster than light. That's also an apparent effect. At the same point in space-time, you cannot have two objects whose relative velocity is greater than that of light. That is the principle of relativity. So there's no violation in any of these things. So thank you for your attention. We can talk some more outside. And I'm here today and tomorrow, and I'll be around. I'm staying in the guest house, and if you want to talk about anything, I'm free. And I'll see you at dinner today evening also.